Introduction and Basic Concepts. This topic introduces the scope and role of thermodynamics in modern engineering. Thermodynamics forms the basis for understanding how energy is stored, transferred, and converted from one form to another. Many engineering systems, such as power plants, engines, and cooling systems, rely on these principles. Understanding the basic concepts is essential before moving to quantitative analysis. The discussion builds a systematic way of thinking about energy and its interactions.
Lesson Plan Thermodynamics 1. The lesson plan shows the learning flow from basic concepts to the second law and entropy. The chapter sequence is designed so students understand the foundation before analyzing closed and open systems. Each topic is connected and forms a unified understanding. This approach builds step-by-step logical thinking. With this structure, learning becomes more systematic and focused.
Learning outcome. The learning outcomes emphasize mastering the basic vocabulary and concepts of thermodynamics. Students are expected to understand unit systems, system concepts, and properties of substances. Concepts of temperature, pressure, and problem-solving approach are also emphasized. All these goals are designed to build a strong foundation before advanced topics. The final outcome is the ability to analyze engineering problems in a structured way. Energy Transformation Overview. Energy can change from potential energy to kinetic energy when an object moves. Although the form changes, the total amount of energy remains constant according to the conservation law. This principle is formally stated in the first law of thermodynamics. The falling object example shows how energy is transferred without being lost. This concept is the basis for analyzing all energy systems. Energy conservation in body. The human body also follows the energy conservation principle like any engineering system. Energy entering through food leaves as work and heat or is stored in the body. An energy balance can be used to explain metabolism in a simple way. No energy is lost, only transformed or stored. This approach shows that physical laws also apply to biological systems. In human metabolism, energy intake equals energy output plus storage within the body. Heat flow principles. Heat always flows from a hotter object to a cooler environment. The rate of heat transfer is strongly influenced by the temperature difference. This process continues until thermal equilibrium is reached. The cooling of hot coffee clearly illustrates this principle. This concept is important for heating and cooling analysis. Solar water heating system. A solar water heating system uses solar energy as a heat source. The solar collectors absorb radiation and transfer it to water through a heat exchanger. A pump ensures proper circulation between the tank and the collectors. This process shows a direct application of energy transfer concepts. The system also emphasizes the use of renewable energy. Thermodynamics applications. Thermodynamic principles are used in energy systems, such as power plants and wind turbines. Transportation systems like cars, aircraft, and ships also rely on these concepts. Even household appliances like refrigerators operate based on thermodynamics. The human body can also be analyzed as an energy system. This shows the wide scope of thermodynamics applications. Fundamental dimensions in SI. The SI system defines basic quantities such as length, mass, and time as the foundation of measurement. Temperature and electric current are added to cover thermal and electrical phenomena. Luminous intensity and amount of substance complete the set of base quantities. All derived engineering quantities are built from these fundamentals. Understanding the unit system is essential for consistent calculations. SI unit prefixes. The SI system uses prefixes to represent very large and very small numbers. Prefixes such as kilo,
Mega and giga are used to simplify large numbers. Conversely, nano, pico, and femto are used for extremely small quantities. This wide range allows measurements from atomic to cosmic scales. Understanding unit prefixes is essential for correctly reading and writing engineering data. Answer C. Iota. Explanation of why other answers are wrong. A. Nano. Incorrect, because nano represents a small scale, specifically 10 to the minus ninth, not a large scale. B. Kilo. Incorrect, because kilo represents 10 cubed, which is much smaller than iota, 10 to the 24th. D. Femto. Incorrect, because femto represents 10 to the minus 15th, one of the smallest scales, not the largest. SI prefixes simplify the representation of volume, mass, and electrical quantities. For example, milliliters and liters simplify liquid volume measurements. Kilograms and grams adjust the scale of mass measurements. In electrical engineering, megaohms are used to express very large resistances. These examples show the importance of SI prefixes in daily practice.
Force unit definitions. Force in the SI system is defined based on the acceleration of a 1 kilogram mass. 1 newton is defined as the force required to accelerate 1 kilogram at 1 meter per second squared. In the imperial system, 1 pound force is defined in a similar way using feet and pound mass. These definitions ensure a consistent relationship between mass, acceleration, and force. This understanding is important for unit conversions between systems. Force units. Comparison. Force units are made more intuitive by using everyday objects such as apples. 1 newton is approximately equal to the weight of a small apple. 1 kilogram force represents the weight of about 10 apples. 1 pound force is roughly equal to the weight of 4 apples. This approach helps build physical intuition about the magnitude of forces. Weight variation on Moon. The weight of an object depends on gravitational acceleration, not on its mass. On the Moon, gravitational acceleration is much smaller than on Earth. As a result, an object's weight on the Moon is about 1/6 of its weight on Earth. However, the mass of the object remains the same everywhere. This example clearly distinguishes between mass and weight. Weight on the Moon is about 1/6 of the weight on Earth due to lower gravity. Weight of unit mass. The weight of a unit mass is defined based on gravity at Earth's surface. In the SI system, a 1 kilogram mass has a weight of about 9.807 newtons. In the imperial system, a 1 lbm mass has a weight of 1 lbf under standard conditions. This shows that weight depends on the value of gravitational acceleration. This concept is important for understanding the difference between mass and weight. Energy from a match. A burning match releases a relatively small amount of energy. This energy is about 1 kilojoule, or 1 BTU. Although small, this example shows the conversion of chemical energy into thermal energy. This simple case helps visualize the scale of energy in daily life. From this, it can be understood that all combustion processes involve energy transformation. Wind turbine. A wind turbine converts the kinetic energy of wind into electrical energy. This system uses a renewable and inexhaustible energy source. The use of wind turbines supports the goal of reducing carbon emissions. This example shows the application of energy conversion principles on a large scale. This technology is an important part of sustainable energy systems. Importance of unit consistency. Every physical equation must be written with consistent units in every term.
Unit inconsistency is often a major source of calculation errors. By checking the units, many mistakes can be detected early. This approach also helps ensure that the results have physical meaning. Unit consistency is an important part of an engineer's working habit. Answer A. The units are consistent because kinetic energy is measured in joules, which is equivalent to kilogram meter squared per second squared. Explanation. The units in the equation Ke equals 1/2 mv squared are consistent because 1 joule, J, is defined as 1 kilogram meter squared per second squared. Mass is correctly measured in kilograms, kg, and velocity is correctly measured in meters per second, m per s, ensuring the units align properly for the calculation of kinetic energy. Conversion ratios. Conversion ratios are used to change units from one system to another. These conversions include force, energy, length, and time. By using the correct conversion factors, the physical value remains the same, even though the unit changes. This method is essential in solving engineering problems involving different unit systems. Careful conversion prevents serious numerical errors. Weight and mass relation. In the imperial system, a 1 lbm mass has a weight of 1 lbff under Earth's gravity. This often causes confusion between the concepts of mass and weight. A scale actually measures weight, not mass directly. This relationship is only valid under standard gravitational conditions. This example emphasizes the importance of distinguishing mass from force. Metric system quirk. In the metric system, grams are often used to represent weight in daily life. Scientifically, grams are units of mass, not force. This habit can cause misunderstandings in engineering and scientific contexts. However, this practice is very common in everyday usage. Therefore, the difference between mass and weight must always be emphasized. System and surroundings. A system is defined as the part of the universe under study. The boundary separates the system from its surroundings and can be real or imaginary. Everything outside this boundary is called the surroundings. Interactions between the system and the surroundings occur across this boundary. Proper system definition is essential in thermodynamic analysis. Closed system features. A closed system does not allow mass to cross its boundary. However, energy can still be transferred in the form of heat or work. Since no mass enters or leaves, the mass of the system remains constant. Many basic thermodynamic analyses start from the closed system model. This concept simplifies the understanding of mass and energy conservation laws. In a closed system, mass remains constant within a system because there is no exchange across its boundaries. Closed system with moving boundary. In some closed systems, the boundary can move so that the volume changes. An example is a cylinder with a piston that can move up and down. Although the volume changes, the mass inside the system remains constant. The boundary movement is usually caused by energy interactions, such as heat or work. This model is important for analyzing piston engines and similar systems. Control volume boundaries. In flow system analysis, the concept of a control volume is used. The boundaries of a control volume can be real or imaginary. These boundaries can be fixed or moving, depending on the system being analyzed. This approach is very useful for analyzing nozzles, turbines, and heat exchangers. With a control volume, mass and energy flows can be studied systematically. Open system characteristics. An open system allows mass to enter and leave through inlets and outlets. Along with mass, energy is also transferred across the system boundary. Many engineering devices, such as water heaters and turbines, are analyzed as open systems. These systems usually operate continuously. This model is essential for flow system analysis. Intensive versus extensive properties. Extensive properties depend on the size or mass of the system. Examples include mass and volume, which change if the system is divided. In contrast, intensive properties do not depend on system size. Temperature and pressure remain the same even if the system is divided. This distinction is important in classifying thermodynamic properties. False. Intensive properties do not depend on system size, like mass and volume. Gas continuum concept. Although gases are composed of molecules that are far apart, in engineering analysis, a gas is often treated as a continuous medium. Even in a small volume, the number of molecules is extremely large. This continuum assumption simplifies the analysis without significantly reducing accuracy. This approach is widely used in fluid mechanics and thermodynamics. With this assumption, fluid properties can be considered defined at every point. Density and specific volume. Density is defined as mass per unit volume. Specific volume is the inverse of density, which is volume per unit mass. These two quantities are directly related to each other. If density increases, specific volume decreases. These concepts are frequently used in fluid and gas analysis. Specific gravities of substances. Specific gravity is defined as the ratio of a substance's density to the density of water. The specific gravity of water is 1 and is used as a reference. Very dense substances, such as gold, have very high specific gravity values. In contrast, air has a very small specific gravity. This concept makes it easier to compare the densities of different substances. A system can exist in more than one state. In this example, the mass of the system remains the same, but the volume changes. The temperature remains constant, even though the volume changes. This state change shows that some properties can change while others remain constant. The concept of state is very important in describing system conditions. Thermal equilibrium in closed system. Initially, the temperature inside the system is not uniform at every point. Over time, heat is transferred within the system until temperature becomes uniform. This final condition is called thermal equilibrium. At this state, no further heat transfer occurs within the system. This concept is important for defining equilibrium states. State of nitrogen. The state of a substance can be determined if two independent intensive properties are known. For nitrogen, for example, temperature and specific volume are sufficient to define its state. These properties do not depend on the size of the system. Once the state is known, all other thermodynamic properties can be determined. This is known as the state postulate. 2. Independent properties, such as temperature and specific volume, uniquely define the state of nitrogen. Process path and states. A process describes the change of a system from an initial state to a final state. The process path shows how the system properties change during the process. On a property diagram, this path connects state 1 and state 2. The shape of the path provides information about how the process occurs. This concept is important to distinguish different processes, even if the initial and final states are the same. Compression process types. If compression is carried out very slowly, the system can be assumed to remain near equilibrium at all times. This process is called a quasi-equilibrium process. In contrast,
Very fast compression causes non-uniform pressure and temperature distributions. In this case, the system cannot be considered in equilibrium. The speed of the process strongly determines the analysis approach.
PV diagram of compression. A PV diagram shows the relationship between pressure and volume during a compression process. At the beginning, the system is at a large volume and low pressure. After compression, the volume becomes smaller and the pressure increases. The shape of the curve indicates the characteristics of the process. This diagram is very important for visualizing work and energy changes.
Steady flow process. In a steady flow process, fluid properties at a given point do not change with time. However, these properties may vary from one location to another. Mass flows in and out at constant rates. Many engineering devices, such as turbines and compressors, operate under this condition. This approach simplifies flow system analysis.
Answer B. Time invariant steady flow. Explanation of why other answers are wrong. A. Unsteady flow. Incorrect because unsteady flow involves changes in fluid properties over time, which contradicts the constant over time condition. C. Adiabatic process. Incorrect because an adiabatic process refers to no heat transfer, not the time invariance or spatial variation of fluid properties. D. Non-uniform transient flow. Incorrect because transient flow implies time dependence, whereas the system described is time invariant. Steady flow conditions. Under steady flow conditions, the mass within the control volume remains constant. The energy balance also shows that the total energy in the control volume does not change with time. This happens because the inlet and outlet flow rates are balanced. This condition allows simpler and more stable analysis. This concept is very important in the design of continuous flow systems. Thermal equilibrium between bodies. Two bodies at different temperatures placed in an isolated system will exchange heat. Heat always flows from the hotter body to the cooler one. This process continues until both bodies reach the same temperature. This condition is called thermal equilibrium. This example shows a direct application of the 0th law of thermodynamics. Pressure-temperature relationship. The graph shows the relationship between pressure and temperature at constant volume for several gases. All experimental lines can be extrapolated to a single common point. This point corresponds to absolute zero temperature. This result indicates uniform thermodynamic behavior of gases. From here, the concept of the absolute temperature scale is developed. Constant volume gas thermometer. A constant volume gas thermometer operates based on the linear relationship between pressure and temperature. As temperature decreases, pressure also decreases proportionally. When extrapolated, the pressure becomes zero at absolute zero temperature. The Kelvin scale is defined based on this point. Therefore, this scale is very important in thermodynamic calculations. Temperature scale comparison. Absolute zero has consistent values across different temperature scales. The triple point of water also has equivalent values in each scale. The Celsius and Kelvin scales differ only in their 0 point. The Fahrenheit and Rankine scales have a similar fixed offset. These relationships make temperature scale conversions easier. Absolute zero corresponds to 0 K on the Kelvin scale. Temperature unit comparison. An increase of 1 Kelvin is equal in magnitude to an increase of 1 degree Celsius. This shows that the two scales differ only in their 0 point. For the Rankine and Fahrenheit scales, the unit size is larger than that of Kelvin and Celsius. This difference comes from the 1.8 conversion factor between the systems. This understanding is important to avoid mistakes in temperature conversion. Pressure on feet.
The pressure acting on the feet depends on body weight and contact area. If the weight increases while the contact area remains the same, the pressure increases. This explains why heavier people exert greater pressure on the floor. Pressure is defined as force per unit area. This example helps visualize the physical meaning of pressure. Pressure gauge overview. A pressure gauge is used to measure fluid pressure in many engineering systems. The instrument usually displays pressure in units such as bar or Pascal. The analog scale allows direct reading of pressure. The threaded connection enables secure installation in the system. This instrument is widely used in industry. Pressure types. Absolute pressure is measured relative to a perfect vacuum. Gauge pressure is measured relative to atmospheric pressure. Vacuum pressure indicates a condition where the pressure is below atmospheric pressure. The relationship among these pressures is very important in fluid system analysis. Misunderstanding pressure types can lead to design and analysis errors. Answer B. Absolute pressure. Explanation of why other answers are wrong. A. Gauge pressure. Incorrect, because gauge pressure is measured relative to atmospheric pressure and does not include atmospheric pressure. C. Vacuum pressure. Incorrect, because vacuum pressure represents pressure below atmospheric pressure, indicating suction or low pressure conditions, not absolute pressure. D. Static pressure. Incorrect, because static pressure refers to the pressure exerted by a fluid at rest and is not defined as being measured from an absolute vacuum. Fluid pressure at depth. Fluid pressure increases as depth increases. This is caused by the weight of the fluid column above the point of interest. Gauge pressure is often used to express this pressure relative to the atmosphere. This phenomenon is very important in the analysis of dams and tanks. This relationship is the basis of hydrostatic pressure. Fluid element in equilibrium. A fluid element at rest must be in force equilibrium. The pressure at the bottom of the element is greater than at the top, due to the weight of the fluid. All forces in the horizontal and vertical directions must balance each other. This condition leads to the basic hydrostatic pressure equation. This analysis is important for understanding pressure distribution in static fluids. Pressure in a room. The pressure difference between the floor and the ceiling of a room is very small. Because the room height is relatively small, the effect of gravity on pressure variation can be neglected. As a result, the air pressure in a room can be considered uniform. This assumption is often used in comfort and ventilation analysis. This example shows when pressure variation can be ignored. Liquid pressure. In a static liquid, pressure increases linearly with depth. The pressure at the free surface is equal to atmospheric pressure. The deeper a point is located, the greater the pressure it experiences. This relationship depends only on the fluid density and the depth. This concept is the basis of many hydraulic engineering applications. Hydrostatic pressure principles. Fluid pressure at the same horizontal level is equal as long as the fluid is continuous and connected. Pressure depends only on depth, not on the shape of the container. If different fluids are used, the pressure at the same depth can be different because of density differences. At the interface between two fluids, pressure remains continuous even though the gradient changes. These principles form the basis of hydrostatic pressure analysis. In a continuous fluid, pressure is equal at all points on the same horizontal plane. Hydraulic jack mechanics. Pascal's law states that pressure applied to a confined fluid is transmitted equally in all directions. This principle allows force amplification using different piston areas. A small force applied on a small piston can produce a large force on a larger piston.
This mechanism is used in hydraulic jacks to lift heavy loads. This example shows a direct application of fluid pressure principles.
Basic barometer function. A barometer is used to measure atmospheric pressure using a mercury column. The height of the mercury column indicates the magnitude of atmospheric pressure. The top of the tube contains an almost perfect vacuum. Equilibrium is achieved when the weight of the mercury column balances the outside air pressure. This principle is the basis of atmospheric pressure measurement. Barometer tube design. The height of the fluid column in a barometer does not depend on the length or diameter of the tube. It depends only on atmospheric pressure and fluid density. The tube diameter must be large enough so that capillary effects can be neglected. If the tube is too small, the reading can become inaccurate. This emphasizes the importance of proper instrument design.
High altitude effects. At higher altitudes, air density becomes lower. As a result, the amount of oxygen entering engines or lungs is reduced. This leads to reduced engine performance and breathing difficulties in humans. This phenomenon is very important in the design of aircraft engines and vehicles in mountainous regions. This example shows the effect of air pressure and density on real systems.
Answer C. Reduced oxygen supply, affecting both engine power and human respiration. Explanation of why other answers are wrong. A. Improved oxygen supply for human respiration. Incorrect, because reduced air density decreases oxygen supply, making breathing more difficult at higher altitudes. B. Increased engine performance due to efficient air intake. Incorrect, because lower air density decreases oxygen intake, leading to reduced engine performance. D. Enhanced oxygen intake for engines and lungs. Incorrect, because reduced air density at higher altitudes results in decreased, not enhanced, oxygen intake for both engines and humans. Gauge pressure in solar pond. If the fluid density is constant, gauge pressure increases linearly with depth. However, in a solar pond, there is a zone with a density gradient. In this zone, the pressure increase is no longer linear with depth. Density variation affects the pressure distribution in the fluid. This example shows the importance of considering property variations in fluids. U-tube manometer. A U-tube manometer is used to measure the pressure difference between 2 points. This pressure difference is indicated by the difference in fluid column heights. The side with higher pressure pushes the fluid toward the other side. The relationship between column height and pressure can be calculated directly. This instrument is simple but very accurate for differential pressure measurement. Basic manometer function. A manometer is used to measure gas pressure relative to atmospheric pressure. Its operation is based on the equilibrium of a fluid column in a tube. The difference in fluid column heights indicates the magnitude of the pressure difference. This method is simple but very reliable for low to moderate pressure measurements. Therefore, manometers are widely used in laboratory experiments. Stacked fluid layers. If several fluid layers with different densities are present, the pressure at the bottom is affected by all these layers. Each layer contributes to the pressure according to its density and height. Layers with higher density contribute more to the pressure. The total pressure is the sum of the contributions from all layers. This concept is important in the analysis of layered fluid systems. Pressure increases with depth depending on the density and height of each fluid layer. Differential manometer use. A differential manometer is used to measure the pressure drop between 2 points in a system. This pressure difference is indicated by the difference in fluid column heights. The density of the fluid used affects the sensitivity of the instrument. With this device, pressure differences in pipes or equipment can be analyzed. This principle is very important in flow measurements. Bourdon tube types. A board-on tube is one of the most common types of mechanical pressure measuring instruments. The tube shape can be C-type, spiral, or helical, depending on the pressure range. When pressure increases, the flattened tube tends to straighten. This motion is then converted into the movement of a pointer needle. This principle is simple but very effective for pressure measurement.
Deadweight tester. A deadweight tester is used to calibrate pressure measuring instruments with high accuracy. The pressure is generated by weights placed on a piston of known area. Oil is used to transmit the pressure uniformly to the system. By adjusting the weights, a reference pressure can be set very precisely. This device is widely used as a calibration standard. Problem-solving technique. A good problem-solving approach should be carried out step by step and systematically. By following clear steps, the risk of errors can be reduced. Overly complicated approaches often make problems harder. Breaking a problem into smaller parts makes the solution easier to achieve. This habit is very important in engineering work. Answer C. It simplifies the process, making problem-solving more efficient and effective. Explanation of why other answers are wrong. A. It skips unnecessary steps to save time. Incorrect because skipping steps can lead to mistakes or complications, rather than simplifying the process. B. It focuses only on complex methods for better accuracy. Incorrect because using complex methods unnecessarily can make problem-solving harder, not more accurate. D. It emphasizes harder methods to ensure no errors are made. Incorrect because harder methods can increase the chance of errors due to overcomplication, contrary to the goal of simplicity. Engineering assumptions. In engineering analysis, assumptions are often needed to simplify calculations. However, incorrect assumptions can lead to significant errors. The example of air pressure in Denver shows the importance of choosing realistic assumptions. Using values closer to real conditions produces more accurate results. Therefore, assumptions must always be evaluated critically. Result verification. Calculation results must always be checked for physical reasonableness. If a result shows something impossible, there must be an error in the calculation or assumptions. A reasonableness check is very important for detecting errors early. This step is often neglected but is crucial in engineering practice. Result verification helps improve the reliability of the analysis. Importance of organization. Neatness and organization are important qualities that are highly valued in the workplace. An organized working environment helps improve productivity and reduce errors. A well-arranged workflow also makes it easier to review analysis steps. In addition, organization reflects professionalism and attention to detail. This habit is very important for an engineer. Tools and skill. Tools such as word processors can improve work efficiency, but they cannot replace basic skills. The quality of the result is still determined by the user's ability and practice. Good tools only make skilled people more productive. Relying on tools without improving skills will not produce good work. Therefore, skill remains the main factor. Significant figures importance. Calculation results should not have a level of precision greater than the input data. Significant figures indicate the precision of a measurement. Proper rounding must follow the precision of the original data. Showing too many digits can create a false sense of accuracy. This concept is important to maintain scientific honesty in calculations. Results should not exceed the significant figures of the input data to maintain accuracy and avoid false precision. References. The references are taken from standard thermodynamics textbooks, widely used around the world. The main sources provide strong theoretical foundations and application examples.
Using credible references is very important to ensure the accuracy of the material. The reference list also allows readers to explore the topic further on their own. This closes the chapter with a clear academic foundation.